Hi Dragan, I'm trying to learn Cytology, today Osmosis, and after we've done it we're going to do martial arts basics training, and if you participate in the martial arts basics training then it's better your own risk. And this is the second part, but we're going to read it again. We came just half a page in. Osmosis is the net movement of a solvent through a selectively permeable membrane. So the total amount of something going through a piece of cloth or something, and the total amount which goes then over. There's also something going back, maybe only the total movement which goes when in total over, subtracted from what has gone back. In living systems, the solvent is water, which moves by osmosis across plasma membranes from an area of higher water concentration to an area of lower water concentration. So at one place there's more water than in another place, and it goes from where there's a lot of water to the place where there's less water. That is called osmosis, if it goes through cell. Another way to understand this idea is to consider the solute concentration. In osmosis, water moves through a selectively permeable membrane from an area of lower solute concentration to an area of higher solute concentration. Now we're talking about solute. So in one area there is more solute, and water goes from the place where less solute is to an area where there's more solute. Because in the area where there's more solute, there is, obviously because there's more else, less of water. There's already a huge chunk taken apart by other things, so there's in total less water. And now water moves to it. But why? Why is it not differentiating between the water and the other molecules? Why is it not seeing them combined? Are there some elements that can mock them, and that water thinks it is water? So water plus some other substance, and water is not going to. So if you're having 30% some substance and 70% water, and here 100% water, is not water still going over it to make them there a little bit more water because here's only 70% of water? Or are there some substances where water is not doing that? Water molecules penetrate plasma membranes and tubes via diffusion through the lipid bilayer, as previously mentioned, and through aquaporins, transmembrane proteins that function as water channels. I think the first thing, I don't know what the word diffusion means that it is just slipping through the plasma membrane, because it's just going through. And aquaporins, that there are some channels, but there's some places the water can go through. They are there to let water through. Osmosis occurs only when the membrane is permeable to water but not to certain solutes. Okay, it is only occurring if water can go through but not the solutes. A simple experiment can demonstrate osmosis. Consider a U-shaped tube, for example, in which a selective permeable membrane separates the tube's left and right arm. So in the center is a piece of paper or whatever. A volume of pure water is poured into the left arm, and the same amount of solution containing a solute to which the membrane is impermeable is poured into the right arm. In the left arm there is the clear water, in the other arm there is water and something else. And that something else can't pass through the membrane or whatever it is. Is wie eardrum to something's permeable and to others not. As a result, the volume of water in the left arm, because the water concentration is higher on the left, here's clear water, there's also something else, and lower on the right, net movement of water molecules, the osmosis, occurs from left to right. So here's 100% water, here's just 70% water and 30% something else, and 30% can't go through, but here's more water wants to go to the place where less water is, so it goes osmosis through. As a result, the volume of water in the left arm increases and the volume of solution in the right arm increases. So by saying there's now more on the left side, on the right side, than on the left side, because the water had gone over. You might think that osmosis would continue until no water remained on the left side. Why is it happening at all? Is it something with the cohesion of water, what it was, or with that you can fill a cup, I think it's called brim, and you can fill a cup over the brim and it's not flowing over for a millimeter or something? Is it because of it? Why is it happening? Is it because water has cohesion, because water attracts other parts of water? And what other parts could mock it? Would it then happen with another thing where water is with the same force attracted to as to other water? In this experiment, the higher the column of solution in the right arm becomes, the more pressure it exerts on its side of a membrane. Pressure exerts on this vapor the liquid known as hydrostatic pressure, and it forces water molecules to move back into the left arm. I don't understand what we mean with hydrostatic pressure. I understand it as gravity. If the water goes over, the right arm goes higher and higher, the gravity is pushing it back. We're saying it is hydrostatic pressure. Equilibrium is reached when just as many water molecules move from the right to left due to hydrostatic pressure as move from left to right due to osmosis. Is it at someday stopping, or is it in an infinite working machine? Have we reached the equilibrium? Because we're saying equilibrium is reached just when just as many water molecules move, not moved, present, move from right to left. Is it forever going on and on? Is it a never stopping machine? What is it even? No little excursion to physics. I heard that particles are moving, and the hotter they are, the more they are moving. I don't know where no hotness comes from, but are they not moving? Is it not an infinite moving machine? Can it not be used to make electricity? Are they not by themselves moving? A solution containing solute particles that cannot cross the membrane exerts a force called the osmotic pressure. Why are the particles that can't go through the piece of paper or whatever are making an osmotic pressure? The osmotic pressure of a solution is proportional to the concentration of the solute particles that cannot cross the membrane. Yes, that makes all sense. If it's there, it is proportional to the amount of it. The higher the solute concentration, the higher the solute's osmotic pressure. Yes, but why is it there, and what is it? Consider what would happen if a piston were used to apply more pressure to the fluid in the right arm. Okay, a piston, that we have it in hydraulic pumps, in hydraulic brakes, so someone is pressing onto it, on one side. Now, what would now happen if someone is pressing on the right arm that has flown outward? With sufficient pressure, the volume of fluid in each arm could be restored to the starting volume. Yes, if someone would press on it goes back to the other side. I want to know how much. And is it not a generation of... That is the same thing as whatever they call it, this, not gas, not dust, not gas, smoke, vapor, these vapor-driven locomotives, these other things, these things with which locomotives drive, if they're heating water, the water is then expanding because it's heated, and then the dust, smoke, gas, vapor, let's call it vapor, is pressing against the hydraulic things, and that is making then the wheel to turn. Because the vapor is pressing against it, and that lifts it up, and that uplifting has been used to lift the wheel one further. Now, is it happening by itself that there is just a membrane separating water into a solute, and it's going over, and that is only the pressure for piston being able to put down? Is it not a pressure putting a piston up? It's certainly very, very little. That is why I would like to have a number. Is it even visible with the eye? It's certainly very, very little. But maybe it happens without anyone doing anything. Consider what would happen if a piston were used to apply more pressure to the fluid in the right arm. With sufficient pressure, the volume of fluid in each arm could be restored to the starting volume, and the concentration of solute in the right arm would be the same as it was initially. Concentration, it is still the same amount of solution there, but it became less concentration because more water came over to it, so it was no longer 30% of 100%, but only 29% because the water amount has risen. The amount of pressure needed to restore the starting condition matches the osmotic pressure. Okay, that makes sense, but why is it called the osmotic pressure? And why is it depending on the solid? Because the solid makes an amount of how much is coming over. What if there's an incredible big amount of water over? Would then the pressure be much greater? About how much energy are we talking? Would it be able to have just 1 gram of solid and 100 tons of water? Would that make then quite a big pressure on just with 1 gram? So another way to think about osmotic pressure is that it is the pressure needed to stop the movement of water into a solution containing solutes when the two are separated by membrane permeable only to the water. We understood what we are explaining here. We're going to read it later again to be really able to explain it ourselves and understand it. Notice that the osmotic pressure of a solution does not produce the movement of water during osmosis. Rather, it is the pressure that would prevent such water movement. Yes, that makes a lot of sense. We don't have found it. We came 2 or 3 sentences further when we did it in the last part. It was the cytology part. If you were here for cytology, you can go directly to the next part of cytology. Then we're going to talk more about cytology. If you stay here and participate in the martial arts basics training, that is very honest. 1 leg up. The other one. Take a leg at the ankle. Tuck the tail on it. Change. 1 foot to the side. And stretch the inner side of the leg. And the other side. And go from side to side. And to the middle. And no, 1 leg up and back. 1, 2, 3. Other leg up and back. 1, 2, 3. The shovel snow plow. And 1 more with your leg. And now stretch kicks. So 1 hand out, kick against it. 1, 2, 3. Hand out and kick. And hand out and kick. And now throw, knee up and back, up and in, up and back, up and in. And now Kreshkin kicks, leg up and back, up and in. And then let's do squat kicks. First lunge kicks. Let's do a few lunges to warm up. So right leg in front and back. Left leg in front and back. And now squat kicks. Squat down and kick to the side. Down and kick. You can do wider squats. Down and kick. And now the lunge kicks. I'm going to kick now close to the camera. So right leg in front, down, up, kick. Left leg in front, down, and kick. Again, right leg in front, down, and kick. And 1 more, left leg in front, down, and kick. And the hiking frog. Squat down, Kreshkin kick. Squat, Kreshkin kick. And swing kicks. Swing over and up. 1, 2, 3. Up, over, 1. And 12 push-ups on the ground. You can do it with the knees on the ground and push up down. You can do a wide push-up, and you can take the elbows to the outside a bit, or you make push-ups, hands underneath the shoulders, elbows close to the rib cage. And number 3, I think. And 5, and 6, and 7. Tuck the table in. 8, and 9, and 10, 11, and and a bit stretching. One heel onto the ground, pull the toes in. Go to the left, pull in, to the right, pull in. Move from left to right, other foot, middle, pull in, right, pull in, left, pull in, middle, move from left to right. Legs to the sides, in and down, down, in and close the legs. And again, that was the martial arts basics training. I thank you very much.